Okay, let's go ahead and finish up section 11.4 with one final example. A mummy was on display at a museum in Niagara Falls until it was sold in 1999. A few years later, researchers identified the mummy as the ancient Egyptian pharaoh Ramesses I. The mummy was eventually returned to Egypt. If 69.57% of the carbon-14 in the mummy remains, estimate how long ago Ramesses I lived. The half-life of carbon-14 is 5,730 years. Alright, so if we want to know how long ago Ramesses I lived, or more importantly, how long ago he died, we're going to be looking for the end of his life. That's the way the carbon-14 dating works. Then we should probably let T be the number of years that have gone by since Ramesses I died. So I'm going to set that up as a starting point. So let's let T equal the number of years since the death of Ramesses I. And then I want to start thinking about trying to make some ordered pairs to put into the calculator that I can use to build the equation. So let's make our ordered pair table. So I'm going to make a function of t where f of t is the percentage of carbon-14 that is left in the mummy. So I'm going to put t and f of t. And one of the ordered pairs that I know is that at the moment that he died and was mummified, there was still 100% of his carbon-14. When somebody's alive, their carbon-14 is stable, but once they die, it starts to decay. So at that moment that the death happened, he was still at 100%. And then, like we typically do in a half-life problem, I want to use the half-life as my next input. So if I put 5,730 as the number of years that have gone by since he died, then I know, because that is the half-life, right, so that's the half-life, that half of his carbon-14 would have decayed away. So he would be at 50% at that point. The other thing that I know about half-life problems is that they have exponential models, exponential decay models. So if I put these two ordered pairs into the calculator, then I can use exponential regression on these to figure out what the equation is. And so to do that, I just want to put this data in. So I'll put the t values into L1 and the outputs, which are the percentage of carbon-14, into L2. And we go ahead and slide this over so we can see both. So I'm going to turn the calculator on, go into the stat and edit modes, and for my list 1 I'll put the 0 and the 5,730, and then L2 I'll put the percentages of carbon-14, 100% at the moment of his death, and 50% 5,730 years later. Once I have that data in, I can use the calculator and the regression feature to get the equation. So I'm going to hit Stat and Calc and arrow down until I get to exponential regression and tell the calculator where my data is, L1 and L2. Press enter and I will get the A and the B. So the function f of t is a times b to the x, where a is 100. That makes sense. That's supposed to be our initial amount, and our initial amount, or y-intercept, was at 100, times the base, and I'm going to put a bunch of decimals for this, 9,9,9,8,7,9, and then the next one's a 0, so I'll go ahead and stop there, and then t. So this was my a and my b, and I'm trying to write a times b to the x, or in this case, since I'm using the variable t, a times b to the t. So now we have our equation, and we're going to try and use the equation to answer their question. So they want to know if currently he has 69.57% of the carbon-14 in his body, or in the mummy, then how long has it been since he lived or since he died? And so this 69.57 is a value of f of t. So I'm going to plug that in for f of t. So in this spot on the left, I'm going to put 69.57. Let me go ahead and slide this back over. So I'm going to put that 69.57 in for the f of t, and that's going to be equal to 100 times 0.999879 raised to the t. And then I'm going to try and use this equation to figure out how many years it's been. So I'm going to think about that real quick over here with the chart. I know it hasn't been 5,730 years, because if it had been, this would be down to 50%. So the fact that this 6957 is between 100 and the 50 means that our t will end up between the 0 and the 5,730. And it's always nice to have at least a rough estimate of how that's going to turn out. And then once we start trying to do our solving, when you're trying to solve for an exponent, the first thing is to get the base by itself. So I would divide both sides by 100 to cancel that off right there, so that the base would be by itself. But if I'm going to divide one side by 100, I have to do the same thing on the other. And normally when I get a fraction like this, I don't like to do the division because it creates a messy decimal that I have to round. But in this case, I'm just dividing by 100, so that's just going to move the decimal over 2 spots. So this will become 0.6957 equals 0.999879 to the t. And you might wonder why I left that space there, but one of the things that you might remember is that if you're trying to solve for an exponent, the way you're going to bring that down is to take a log. So I'm going to want to take a log of this to bring that exponent down using our log properties. If I take a log of one side, I need to keep things balanced and take the log of the other side as well. So again, the reason I do that is we have the log property that says when you have an exponent on the inside part of a log, that can be brought out front as a factor. So I'll copy the left side, log of 0.6957, and on the other side I'm going to bring that t out into the front. So t times the log of 0.999879. And we're almost done. And we won't have to write that messy decimal too many more times. We want this t by itself. This log is connected to t by multiplication, so I can get rid of that by doing division. So when I do this division right here, these logs will cancel and t will be by itself, but like always we want balance, so if I divide the right side by that log, I need to divide the left side by that log as well. And now we basically have our answer for t. T is going to be the log of 0.6957 divided by the log of 0.999879. And at this point I would go ahead and just try and get an approximation for that in the calculator. And so let me go ahead and slide this over so we can see that for entry. So I want the log of 0.6957 divided by the log of 0.999 and 879. When you do a log on the calculator, it always opens a parentheses. Make sure you close it when you're done with that log, so otherwise this other stuff gets inside of the first log. So I have this log divided by that log. I'm expecting an answer bigger than 0 and less than 5,730. So 2,998.46 fits into that. And I guess if I'm going to write two decimals, since that's a 6 followed by a 9, I'd write 47. Typically we round these things to the nearest year, so if I was to do that, I'd say, so t is approximately 2,999. And they asked how long ago he lived. If I read this problem correctly, this 69.57 of the carbon-14 in the mummy was how much was there in 1999 when that was checked. And so I would say that he died 2,999 years before 1999. So he died 2,999 years before that carbon-14 test in 1999 occurred. I guess we could try and work out the year and say it's about 1000 BC, but I don't even think that's really necessary because they didn't say what year was it that he died. They asked the question, where was it, how long ago did he live? So he died or lived 2,999 years before the carbon-14 test in 1999. I guess it's a little weird to say died versus lived, but when they ask how long ago he lived, they're kind of asking how long ago did he breathe his last breath, and that's going to be simultaneous basically with that moment he died. So I think we could answer that question either way and it would make sense.